Welcome back. Welcome back. Today, again, your guide, your mentor, your teacher, your helper, whatever you can say. But yes, today we are going to discuss in this video about the circuits. As you can say, DC and AC circuits. But in addition to this, we will discuss in this video about electrical and magnetic circuits along with the transformer. So remain in a video. Okay, be in a video and because as I received certain requests that yes, we have to think, we have to go with a practical approach. So I will definitely take care of the practical approach in this video. So keep in touch, keep seeing this video till the last. Thank you very much. So let's start. Today we are going to discuss introduction to DC and AC circuits. And when I talk about DC and AC circuits, we have to understand there's a very small difference between DC and AC. And sometimes this question is asked in various interviews that yes, what this DC and AC circuit is all about. So when I say you that DC and AC circuits, you need to understand two, three things. What are the two, three things? You have to see that DC and AC are being segregated, differentiated by a concept of a frequency. So if you have a frequency, right? If you have a frequency, that means you are dealing with the AC, and if don't have a frequency, you are dealing with the DC. It's simple as such. Okay, and one more thing that we want to say about it, that whenever we are talking about DC and AC, we have to understand again many ways that yes, if AC is there, right? If AC is there, so that actually we are dealing with a frequency, and the frequency can be 50 hertz, 60 hertz, 48 hertz, depending on the country you are living in. And DC is basically is without frequency. The frequency is zero in the case of DC, and DC is more dangerous as compared to AC, right? So there are certain basics we are going to deal, and in this video we will go with DC and AC circuits. We will go with magnetic circuits. We will also deal with transformer with a practical approach also. So keep in this video till the last. So these are lecture objectives, what we were going to have. So students aware about the basic and separate DC and DC circuit, aware about the electricity. So whenever I say about electricity, you need to know two, three things again, that electricity is a weightless thing, right? And easy to transport. So we will also deal with the different types of electricity, wireless electricity nowadays we're talking about, and those are with CSE branch. They might know that when we're talking about wireless electricity, we are talking about without wires, and there's a very what I can say ambitious project of NASA, and they're working on it from the last 10 years, and already they completed many infrastructure, and they're working on it. So we will also deal with different type of supply, AC and DC supply, how they will look after, and different type of sources. And in last, we will discuss about the Ohm's law. So when we talk about importance of basic electrical electronics engineering, this question normally asked because in this video we will talk about electrical electronics only. So this question normally asked if we are from this branch, CSE branch, or mechatronics branch, or mechanical branch, or some any other branch, and they ask that why we are going to study this basic electrical electronics engineering. So first of all, you have to understand the difference between electrical and electronics. Electronics deal with low voltage, electrical deal with high voltage, but electrical is a parent branch. In abroad, you can see we deal with electrical and computer, we deal with electrical and mechatronics, we deal with electrical and automobile engineering. But in India, we only deal with the parent branches. But the time will come because right now we are going to implement NEP, National Education Policy. I have one video, National Education Policy. You can go and check out how it will going to help you out. So the electrical is basically going to use in industrial plants, in communication, satellite navigation system, electronic equipment, medical appliances, and product designing and development. So these are the contents and why we need electricity, why there are different type of electrical elements, what are the type of elements, active and passive. We will go a little bit in detail. What are active elements, what are passive elements, what are their examples. We will also go with the differences between AC and DC supply, different type of sources, and in last we will discuss about the Ohm's law. Let's start now. Electricity, yes, already discussed with you all that it's a most versatile and easily controlled form of energy. When I say easily controlled form of energy, it means that we are able to generate. We have generators, we have alternators. So when I talk about generators, they are generating DC supply, and when I am talking about alternator, they are generating AC supply. That is very, very important. You have to understand. Okay, so we also require electricity to turn on our computer, refrigerators, right? And when I talk about computers, you might you see that we are having a 3-pin switch, and this 3-pin switch required in every electronic devices. And in your desktop, we are having SMPS, switch mode power supply. In refrigerators, yes, we require And this question is also asked in some of the interviews that why we require same voltage. Why I'm emphasizing on these basic points. See, in a whenever you are from CSE branch, whenever you are from mechatronics branch or any other branch, the thing is, you have to make certain system from you with a human interface. And when we deal with human interface, we require certain basic things. It's like if you are making some kind of a computing device or some kind of algorithm which deals with voltage and current, which deals with certain physical quantities. So you need to understand little bit basics. Otherwise, how you will optimize them, right? So we require voltage. We have a voltage parallel in every circuit, and we keep same because for appliances we require because voltage is an independent quantity. We also dealing with electric vehicles. Nowadays we are so much emphasizing on electric vehicles. Right, basic electrical elements. There are three basic electrical elements: resistance, inductance, and capacitance. When I talk about resistance, it is opposition to the flow of current. But on the other hand, and it's a bilateral element. From the both sides, the current can flow. But when I talk about inductor, as you can see in front of you, the inductance is basically the opposition to the rate of a flow of current. Please remember this. Resistance is the opposition to the flow of current, but inductance is the opposition to the rate of change of current. We will go a little bit more in video and you will see yourself that how the inductor and resistor is separate. But yes, inductance is dealing with the magnetic field, and resistance can be active, can be passive, depending on the kind of configuration. If we are talking about rheostat, yes, it is a passive element, but when we are talking about a simple structure, it's a active element. And we have a capacitor. Might you all of you are having an inverter in your home, and you might see that whenever you're turning on inverter, you will experience some kind of noise in your fan. The reason behind this, because see, whenever you are dealing with this capacitance, capacitor block DC and allow AC. It doesn't mean because see, capacitor in between you can have we have having a dielectric in between these two plates, right? And when I talk about this dielectric, we are having four different type of materials. One is conductor, semiconductor, insulator, and dielectric. And semiconductor is an insulator at a room temperature. So you can see the unit of this capacitor is farad, and the unit of inductor is Henry, and the unit of resistance is ohm. Again, that's very, very important. So capacitor, whenever you require any kind of capacitor in your fan, and whenever inverter turned on, you will have AC and DC mixture. It won't be a pure AC, it won't be a pure DC, it would be a mixture of AC and DC. And DC would be blocked by a capacitor, and you won't get a proper supply, proper input, and that's why you will get certain kind of noise. So we are having current also. So electric current, you know very well, rate of flow of electric charge through a conducting medium, and the unit is ampere. The SI unit is ampere. I'm again repeating, SI unit is ampere. When we are having electric potential difference, we know we are having three different types of voltages. You can see my expressions. We are having three different type of voltage. One is terminal voltage, second is potential difference, and third is your voltage drop. Ohm's law talks about your voltage drop. It won't tells you about potential difference or terminal voltage. But yes, when I'm talking about potential difference, we are talking about bringing a charge from infinity to a certain point. That is your electric potential. And whenever you are having two different terminals, that this potential is different, the current will flow from higher potential to lower potential. We will see more in this video that how the current will flow from positive to negative and negative to positive, and what is positive and what is negative polarity. So keep seeing this, and because in this whole video I keep various topics intact, because this was a request from the students that keep all the topics whatever related to circuits keep in one video. So if you want a different videos, I can do that. So we were talking about electric potential difference, amount of work done to carrying a unit charge from one point to another point in electric field. Similarly, voltage, we talk about voltage, it is exactly the same as we can see, it's a voltage source, right? Resistance is connected in series. Don't get confused that resistance is connected in parallel. No, it is connected in series. Series means when the current is same. We are having a different type of elements: active, passive, linear, non-linear, unilateral, bilateral. So when I name about active, as I'll discuss with you, the active elements are those elements which have their own source of energy. So when I say when they are having a own source of energy, it means that voltage source, current source, it can be transistors, it can be NPN transistor, PNP transistor, doesn't matter, but they should have their own source of energy. Similarly, when I talk about passive elements, You can see they don't have, they require external source of energy for their operation. It can be resistance, it can be inductance, it can be capacitance. I hope this is clear. We also talk about linear elements. When we talk about linearity, see, there are two kind of principle. One is superposition, one is homogeneity. So superposition principle says that yes, whenever you are having input and output, the both quantities should remain have a same level, right? This actually means by homogeneity or superposition. So superposition says if we are replacing input by output, the circuit should remain same. That is your superposition. Homogeneity says that if the whatever the quantity has input and output, they should have the same dimensions. But linearity is just different from them. Don't confuse yourself. Linear element is one in which we talk about the linear characteristics. It has to be drawn between the graph and between the input and output. So how you will decide that x-axis and y-axis? On x-axis, always an independent quantity will come, and on y-axis, the dependent quantity will come. So you can see non-linear elements are vacuum tubes and transistors, whereas your linear elements can be inductor, can be capacitor, can be a resistor. The unilateral, we discuss about it, right? What unilateral element is? Unilateral element is those elements in which the current will flow in one direction, like a diode, like a transistor. In the bilateral, no, the current can flow in any other direction, both directions. So it can be resistance, it can be inductance, it can be capacitance. Right? So any kind of queries till this point, you can comment in a section. The type of supply, we also discussed the type of supply. We are having an AC supply, we are having a DC supply. So you can see what I wanted to convey to you. You can see positive, the current is flowing from high potential to lower potential. Whereas in this case, in negative polarity, the current will flow from positive to negative. So naturally, the current direction is opposite. So over here, clockwise and anti-clockwise is very, very important. So when I say clockwise and anti-clockwise, you need to remember two things more. When I say clockwise, it will the rotation is basically of generator, right? When I'm talking about clockwise, it's a generation, it's a clockwise direction, that means generator. When it is anti-clockwise, it's a motor. So you will study in a machine video, but right now it's just a little bit concept, right? So the current and that changes magnets of polarity at regular intervals of time. It's a alternating current. You can see now DC supply, we are having a battery. And when I representing battery, when I showing battery over here, you can see we are having an even number of plates. That is very, very important. Again, the battery will have, or the source will have always even number of plates. It won't have an odd number of plates, right? But whenever I talk about odd number of plates or odd kind of, it can be earthing. So you have to very much clear about it, what kind of source I'm talking about, right? So in this, you can have a meter, you can have switch, load, and voltmeter, right? The difference between the AC and DC supply, you know very well the definition. That is the direction of current reverse periodically, and it remains same frequency 50 or 60 hertz. It can be 48 hertz also, depending on the kind of country you are living in. Okay, obtained from alternators, AC supply, DC supply applied to generators, sajators. Yes, DC is very, very dangerous. Okay, so that we discuss. So we also discuss the type of sources. There are different type of sources available with us. So you can see we are having voltage source, we are having current source. It can be ideal voltage source, it can be practical voltage source, it can be ideal current source or practical current source. So when I talk about ideal, it means that it does not have any kind of resistance. In practical, we will see that we will have resistance and we won't have a constant voltage. In the other way, in ideal case, yes, we will have constant amount of current or constant amount of voltage when we have a current source or voltage source. You can see two different type of sources in front of you. One is representing positive, negative, so it is basically DC source, and one is representing wave, so it is having a AC source. So by seeing it, you can even identify what kind of source you are dealing with. Current source, you can see current source is representing by a symbol and the resistance is connected in parallel with it. Whereas if I want to make a voltage source, the voltage source would be connected, same resistance would be connected in series with it. So whether it's electronic or whether it's electrical circuit, but normally your current source or voltage source is electronic circuits, not electrical circuit, right? Then we talk about ideal and practical voltage sources. You can see the constant voltage is there, and in the practical voltage source, there's some kind of deviation due to the resistance only. So the ideal voltage source, other name of ideal voltage source is also known as independent voltage source that does not depend any kind of current. Even so, ideal current source, again, it develop a constant amount of current, but yes, deviation would be seen in the practical current source. So now in front of you, we can see that we are having four sources. And when I say four sources, you have to be very clear about it. See, first is voltage controlled voltage source. You can see 6 Vs, that is voltage controlled, is a voltage source. As you can say voltage source, but who is going to control? Current. So it's a current controlled. Similarly, you can see it's a current source, but who is controlling? Voltage. So voltage controlled current source. Similarly, 6Ix, that means it is controlled by current and it's a current source. So four different type of sources we have that we can be used in different type of circuits. We have independent sources which cannot be which can be only converted from voltage to current source, that cannot be converted into different type of sources. Like if I talk about dependent sources, they cannot be converted. So we are having independent sources whose output does not depend on any kind of circuit parameters. You can see application of AC supply. We have motors, generators, refrigerators, dishwasher, transformer. These we normally use AC supply. You can see cell phones, flashlights, DC supply in your batteries, in solar PV system, laptops. We already know what are the advantages of AC circuit over DC circuit. So AC is very easier than the DC supply. We know that, and easy to generate. AC losses are very less. Efficiency is good of the AC generator. So then we are talking about Ohm's law. So Ohm's law, we know very well that what Ohm's law is. Ohm's law deals with the voltage and current relationship. You can see that when we are having a V and I relationship, we will get a linear relationship in the terms of Ohm's law. And this is the relation V upon I1, V2 upon I2, Vn upon In is equal to constant. This constant is also called as resistance. You can see the potential difference across it, and there is some limitation of Ohm's law. It is not going to apply in unilateral. It is not applied to non-linear. It is not applied to non-linear network, and that we discussed. So this is all from my side. Any kind of query you have, you can ask me. Right, certain questions. Thank you very much. So now students, we were understanding about the AC and DC circuits. Now we will talk about introduction to Kirchhoff law. That will go a little bit more in detail about Kirchhoff law. The second topic what we are going to discuss is Kirchhoff law. And after this, we will go with the AC and DC circuit having series RLC or parallel RLC. Okay, and we will discuss about what is the significance of RLC circuits into it, right? So we will go with the Kirchhoff's law. What's Kirchhoff's law? We will see that example of Kirchhoff's voltage law and Kirchhoff's law. So we will go with the contents also. Introduction to Kirchhoff's law, different terms used in Kirchhoff's law, Kirchhoff's current law, example based on KCL, voltage law, KVL, KCL. So what we need to understand KVL and KCL is, KVL is all about the mesh law. Don't confuse yourself. KVL is basically associated with mesh law. When I'm saying mesh law, you need to understand that there is a difference between mesh and loop. Okay, mesh is the smallest form of loop which cannot be further divided. Loop is a closed circuit. So KVL is going to apply in a closed circuit, whereas KCL is going to apply in a circuit where the node and junction would be there. So in front of you, just the introduction of these laws, that these laws will help in calculating the electrical resistance of a complex network. Okay, and with the different streams of the net, definitely. So we will go towards it. You can see terms during the Kirchhoff's law. We are having a node, junction, branch, loop, and mesh. They are the 5 different terms which will help you to understand Kirchhoff's law more significantly or in a more better way. Okay, so what we are going to discuss now, node. Node is a point where 2 or more circuit elements are connected, very right. And in junction, where the 3 or more circuit elements are connected. But over here, you need to understand what elements are. Okay, see, if I'm going to draw a particular, I will discuss in a later slide. See, if 2 or more branches or 3 or more branches, you will be confused. So remember one thing, wherever we are having a node, we will have a junction, but wherever we will have a junction, we won't have a node. Not necessarily, it can be, but not necessarily. But wherever we will have a node, where we have a junction. And when we talk about elements, it's not about elements, it's about branches, right? And closed and loop and mesh, we already discussed for a closed path. So we can say first law, second law, according to junction rule, according to the mesh rule, and also so many names are given with the for the Kirchhoff's laws. You can see easily Kirchhoff's law states that algebraic sum of all the currents meeting at a point or a node point. Now, over here you will be confused if you will talk about two branches, three branches, because the statement says the currents at any node point or a junction. Please believe me, currents at any point or any node point or a junction. That means over here he is saying node and junction. So you have to very much clear that what is node and what is junction. So that's why I gave you in the start that every node will have a junction, but every junction will not have a node specifically or necessarily, right? So every sum of all currents you need to remember. So incoming current would be positive and negative current would be negative, or a vice versa, but for a particular circuit. It cannot be like if you're saying the voltage, if you're saying the current, or if you're saying something else, it cannot be. It cannot be means you cannot go like this that okay, if I'm talking about that the current is same or current is more or current is less. So if in one circuit you're talking about current is incoming current is positive, in one say you are saying current is negative, that is not possible. So you have to keep your current, incoming current positive or outgoing current negative or vice versa, but should be same, should be have a same proportion, should have a same symbols in whole circuit. So considering the above figure as per Kirchhoff's current law, you can say I1 plus I2 minus I3 minus I4 minus I5 plus I6 and can be anything. So in short, the sum of current, incoming current, it should be equal to sum of outgoing current. Now let's have a one numerical because most of the students told me, sir, please solve the numericals also. So I'm taking some numericals for your consideration. Just see to it. You are having many currents. You can see three currents are entering, four currents are entering, and one current is going outside. You can see I1 plus I2 plus I is equal to I4, and I need to be known. So you can easily say I is equal to 1 ampere minus 1 ampere. That means the current which you calculated is basically your outgoing current. I hope this is clear. You can see I plus I3 plus I2 plus I1 should be equal to I4. I hope this is clear. So that's how you can solve the numericals. Similarly, second numerical you can see we have to find the I2 current. So what I will write, I3 plus I2 should be equal to I1 plus I4. We will calculate, and similarly we are getting a positive value of current. So we will say the positive value of current, that means that's the incoming current. Similarly, numerical based on Kirchhoff's current law. Again, one more numerical. You can see there are three currents which are going outside and one current which is coming inside. So you can calculate and you can see that incoming current is positive. So that means the direction which we consider was right. I hope this is clear. Now we will talk about Kirchhoff's voltage law. As you can see, multiple batteries are connected over here, and the formulas would be seen side by side. You can see V1 and V2 in which two resistances are connected, and these two resistances are in series position. Just see to it. These two resistances position are in series, and there's a voltage. So I can say R1 plus R2, and I can say V1 plus V2. But don't confuse yourself, because what KVL says sum of voltages. It can be E, it can be V. So don't confuse again. Capital E is basically the voltage which is written on a drive cell. And when I say small e, it is nothing but your induced EMF. So capital E is a voltage which is taken care by, not a problem, which is taken care by, but that is a maximum voltage in an open circuit condition. I hope this is clear. And V, capital E, is a voltage which is taken care in a closed circuit condition. So there is a difference between both of them. But if I'm talking about small e would be induced EMF and small v would be instantaneous voltage. I hope this is clear. So this is your KVL in which we are talking about algebraic sum of all the voltage in a closed circuit should be 0. Now you can see already it has been written. So I'm not going to go in detail about it, but it is also known as mesh law. Now we will go with certain kind of symbols. You can rewrite the equation. You can see the two batteries are connected. Just see to it, positive and negative end. This I'm talking about positive and negative ends are being connected. You can see this positive and negative ends are being connected together. So we will see what we can do. Now you can see I'm talking about minus V1 plus minus V2. That means if your batteries, I'm going again back, if your two dissimilar, what I can say, uh, plates are being connected, then it would be added. If similar are connected, it would be subtracted. Same means subtract, dissimilar means add. Okay, so you can see V1 plus V2 divided by R1 plus R2. Simple formula, no need to say. They are saying they are having multiple batteries, say 3, 4, doesn't matter. It depends how your positive and negative plates of the battery are connected. Now you can see in this we are having two similar plates are being connected. In between we are having a resistance also, doesn't matter. Okay, but it will go like this. Why it will go like this? Because you can see that there are two dissimilar plates are been there. So you can see V1 minus V2, all the resistances are in series, R1 plus R2 plus R3. Right? So this is how we can see the direction of current and direction of voltage, or the polarity of the voltage element. So you can see one numerical. Find out the voltage in the figure. You can see plus 5 volt and plus 3 volt. How they are connected? They are connected in a different way. So I will say 5 minus 5 minus. Then actually I will go with C. They are dissimilar metals. No, they say the same plates are being connected. So 5 plus 3. Right? In the next question, you can see we need to only calculate. So 6 volt is equal to 3 plus 2, that is 5 ampere. You can easily calculate and you can get the value of current also. So they are very simple numericals. You can get in 2 marks question, or you can get in some multiple choice questions, or you can get in some competitive exams for the same. Okay, so you can see apply voltage in the KVL circuit. You can see positive and negative are connected. So it would be 6, right? Positive and negative are basically opposite connectors. 6 plus 2 and V, how they're connected, again the dissimilar. So it would be what? It would be plus minus 4, because it would be in opposite. So you can see the V is coming to minus 5 volt. That means the band plate, so the battery has to be connected in a different way. I hope this is clear. Evaluate the voltage across this, again 5 volt and 3. You can see 5 and 3, how the dissimilar are there. So we will add them. And the current is total resistance total 5. You can easily take it, and the voltage is 8. So you can get 8 by 5. So different with KCL and KVL. KVL deals with conservation of energy. KCL deals with conservation of charge. Applicable closed path at node. Now you would be surprised to see at node. Otherwise, node and junction are very, very critical points. Otherwise, you don't have to confuse yourself, right? So keep only this point, that wherever we are having a node, we will have a current divide, and wherever we have a junction, the current would meet, or the current will don't divide, we won't divide. So remember, every node is a junction, every junction is not a node always. So we can evaluate all the voltage and current in a circuit. We can also calculate how the current and voltage work in a circuit. Frequently asked questions can be there. Some practice question I am sharing with you. You can see in the first question, if you need to calculate the current in 2 ohm circuit, what you need to do is you can apply mesh analysis. This is the one mesh, the second mesh. So 28 volt is equal to 4i1 plus 2i1 minus i2. And in this case, if I talk about 7 is equal to if I say this is I2, so I2 plus I2 minus I1 into 2. Similarly, you can calculate 2 equations would be there, and you can easily solve them. Similarly, in this question, if you're talking about this 24 ohm resistance, you can easily apply nodal analysis, and you can easily solve VA minus this about this and this about this. So VFC, if we're talking about node analysis, VA minus, always consider the node potential at a higher side. So VA minus 12 divided by 49, VA minus VB always has a zero potential. VA minus 0 upon 24, and VA minus 6 divided by 80. Right? So I will take all the currents equal to 0 and we'll equate them and we'll solve them. So this is how we are discussing this thing. So this was about KVL and KCL. Second topic. So now we discuss what? We discuss about introduction about AC and DC circuits, and we also discuss about Kirchhoff's law. I hope this is very much clear to everybody. If any comment about this topic, you can reply to me, or if you ask me, I can make different videos for different topics. I'm making all the videos, all the topics in one go only. You can see, right? The background is same, my attire is same, everything is same. So I'm coming back to this now. So we are going towards the third topic, that is again DC and AC circuits. But in this, we will go with RLC circuits. We will go with the series connection of RLC circuits, and we'll discuss a little bit overview of parallel RLC circuits. Now, if I talk about series RLC or parallel RLC circuits, you need to understand one thing. This RLC, we never connect this LC circuit separate. Otherwise, if we are going to connect LC circuit separate, it would be an oscillator circuit, and the another name of this oscillator circuit is tank circuit, right? So we normally don't name it like this, a tank circuit, or we don't normally connect L and C in parallel because it will go with the oscillation, under-damped oscillation, over-damped oscillations. So we normally connect RLC in series or RL and C in a parallel in such a way that the oscillation should not emerge, right? So we will go with this in this topic. We will go with the all the RLC circuit, because one of the students told me, said don't divide this particular videos, just make all the topics in one particular video. So I'm just considering this. If you want different videos, I will divide in them and will share with you, right? So there's not a problem. I hope this is clear. Okay, so without wasting another much time, because we are already getting short of time for our topics, because we are left with so many topics already. So I will go with the third topic now, that is your introduction to DC and AC circuit, in which we will discuss about RLC circuit. So you can see RLC, in which bulb is there, and mostly the question was is asked that we are having a 0 watt bulb, how the 0 watt bulb work, what is 0 watt bulb. So here we talk about different type of powers, real power, reactive power, and apparent power, that you will see over here. And we will see also the phasor diagram, which is very, very important from the theoretical point of view and from the numerical point of view. So we will go with this. Now let's see series RL circuit. Now here we are only connecting RL circuit in a series combination. As you can see, the R and L. So remember one thing, whenever these kind of circuits are given to you, don't add the voltage of R, that is VR and VL, as a algebraically. These are not, this cannot be connected algebraically. This is a vector sum. This is your vector sum, right? So because VR and VL will behave in a different way. You will see the phasor diagram when I will see, when I will show you. Now you can see they are series circuits. So current and voltage and current are in same phase, or we can say IR and IL are same. So when I am talking about V, we are giving us AC voltage, V is equal to Vm sin omega t, and VR and VL are being connected over there. You can see in VR, we are having a VR and VL. So resultant is nothing but impedance, right? You can see the formula now in front of you. From the phasor diagram, it is very clear. The V is equal to the resultant V is nothing but the VR square plus VL square. This is your perpendicular, this is your base. So VR square by VL square, IR square plus IXL square. We take I out, it will become R square plus XL square. So in other words, this R square plus XL square is nothing but known as impedance. And this is Z is equal to nothing but under root of R square plus XL square. This is very, very important. Okay, because in certain question, you will be asked to only calculate the impedance only, right? So if you talk about phase angle, now again the phase angle, you can see from the same phasor diagram, tan phi. What is tan phi? What is tan? Perpendicular upon base. So what is perpendicular? Your VL. What is base? VR. So it would be VL upon VR. What is VL? IXL. I'm talking about the drop, voltage drop across inductor. I'm not talking about anything with voltage across inductor. I'm talking about voltage drop across inductor. So it is IXL. The I would be cancelled because it is same. So it would be XL upon R. So phi would be tan inverse XL upon R. But if you want to calculate the power factor, again, very, very important, cos phi is nothing but base upon hypotenuse. What is base? IR. What is hypotenuse? IZ. So it would be IR upon IZ. That is, you cancel I, that is R upon Z. So these three formulas are very, very important whenever you're going to calculate any kind of numerical is involved for the RL circuits. Let's move to RC circuits. In RC circuits, what we are going to do, we are connecting R and C in a series. Right? I already told you we don't connect L and C in series, we don't connect L and C in parallel, and we connect R always. So R and C is connected now. So V is equal to Vm sin omega t. Again, the phasor diagram, if you will see in the capacitor, your voltage will always lag, current will lead. But in the case of your L circuit, RL circuit, as you can see the later phasor last phasor diagram, in which the voltage was leading but the current was lagging. So you can see now The V is nothing but VR square plus VC square. So I would be taken out R square plus XC square. So impedance is R square plus XC square if R and C are connected. In RL, it was under root of R square plus XL square. Similarly, the phase angle, you can say the XL upon XC, XL upon R in the RL circuit. In this case, it will be XC upon R. Similarly, the power factor. Now, the power factor, the value of power factor will remain same, whether it's RL, whether it's RC, right, or whether it's RLC. So power factor will remain same, but the phase angle will is going to change with the kind of circuit you are using. And value of the power factor will remain between 0 and 1. Now you can see we are going towards large circuit now, that is RLC circuits. In this RLC circuit, you can see RL and C are connected in series. So when this RL and C are connected in series, you can see now that in this case, I am having RL and C connected in series in such a way that the voltage cannot be added. Again, I am repeating, VR, VL, and VC cannot be connected, cannot be algebraically connected. It would be different. Okay, so because as we already know, the L is basically magnetic circuit, C is passive element, R is somehow active, somehow passive, so we cannot add the voltages. Otherwise, in series also the voltage won't be same. In parallel, the voltage would be same. So you can say IR is equal to IC is equal to IL. See, over here you will have VR. Okay, this is your VL and this is IZ. So naturally, when I talk about resultant, it would be VL minus VC. So Z would be your R square plus XL minus XC whole square. That is very, very important. Okay, the impedance is root of R square plus XL minus XC whole square, where XL is nothing but omega L 2 pi FL and XC is equal to 1 upon omega C 1 upon 2 pi FC. So I already told you the power factor remains same, cos phi is equal to R upon Z, but in the case of phase angle, it is XL minus XC divided by R. Right? Is this clear, I guess? So what we discussed about analysis of RLC, phasor series, phasor of series RC, RL or RLC circuits. So these are some questions normally asked. In a series RL circuit, VL lags or VL leads. You know very well in RL, the VL is going to, yes, lead. And whenever we are talking about voltage applied across RL circuit is equal to, we know that it is a phasor sum. It's a phasor sum. It's not algebraic, not an arithmetic sum. Power factor will lies between 0 and 1. This is one question. You can see the capacitor is having capacitance. XC is given. Okay, with non-inductive resistance, R is given. So what kind of circuit it is? RC. Across how much volt? 100 volt, 50 hertz supply. So VM is how much? 100. So you can easily calculate the phase difference in power. Is this clear? I guess everybody is clear. Again, it's a humble request from my side. If somebody is having not a clarity is not there, you can write in the comment section. I would love to answer your questions. Yes. So any kind of question you can ask me, Bacha. You can write in the comment section. Right. The another topic we are talking about now, we're talking about introduction to magnetic circuits, and this is again a very, very important topic. In fact, after your RLC circuits. So when I'm talking about introduction to magnetic circuits, you can see that we are going to discuss about magnetic circuit a little bit more detail. And we will discuss about the introduction to magnetic circuits. We will talk about magnetics, motive force, magnetic flux, permeability, different quantities, and how they are going to help us. This is a totally theoretical topic, but we will go a little bit more, what I can say, with examples. We will try to understand, right? So let's start now. We will talk about magnetic circuits. We know what is magnetic circuits. In magnetic circuit, first of all, very important, you have to understand, in magnetic circuit, we don't have any insulator. In electrical circuits, we do have, but in magnetic circuit, we don't have any insulator, sorry. So the closed path followed by the magnetic lines of force is called magnetic circuits. So it starts on one end and ends at the same point after completing its path, whereas in the electrical circuit, it was not the same case. So in the magnetic circuit, we were talking about flux. In electrical circuit, we are talking about current. So depending on the flux, we are having two different types of magnets. One is permanent magnet, one is electromagnet. Electromagnet is one in which the current starts flowing through it. and then it will become magnet, and permanent magnets remain permanent magnet. And this kind of magnets are used, permanent magnets kind of magnets, they are used in your motors or machines. In magnetic circuit, different materials, we are having ferromagnetic, ferrimagnetic, paramagnetic, or diamagnetic materials. And we can see these magnetic circuits are used in various devices like electric motor, transformers, relays, galvanometer, and generators also. You can see this very simple magnetic circuit. Exactly, it is a circuit of transformer in which you can see we are having a primary turns over at winding and turns, and we are having a magnetic flux of lines of force. Here there is an air gap and magnetic core permeability, which is decided by the type of material you're using for the magnetic circuits, and cross-sectional area is basically the mean length is here, right? So basically, you have to understand whenever we talk about a magnetic circuit, the transformer is having a maximum efficiency. The transformer is having a maximum efficiency, right? So in the case of terms in the magnetic circuit, talk about magnetic field. Magnetic field is the region around a magnetic material or a moving electric charge, right? Which is the force of magnetism acts. Magnetic field lines, yes, these are basically imaginary lines, but yes, they shows us where the magnetic field occurs. So these lines are basically visual to represent magnetic field. So but what important is magnetic field, which is the region around a magnetic material. Then MMF is very, very important. Magnetomotive force. It is just similar to the EMF, that is electromotive force that we are having in electrical circuit. And this magnetic pressure, which is set up by the magnetic flux, so the magnetic circuit is called magnetomotive force. So units is basically SI unit. That is very, very important. In your competitive exams, this question can be asked. The SI unit MMF is ampere turns, but in the case of a CGS unit, that is your Gilbert. Okay, so keep remember this. There are two different type of units we have. So one is your Gilbert, that is a CGS unit. SI unit is your ampere turns. So terms using magnetic circuits in which we are having magnetic field, current, and magnetic pole are there. So terms in magnetic circuit, F is equal to Ni. This is a very important formula. You can see magnetic coil in which the current is start flowing through it. We have a magnetic pole. Number of turns are around it. So this will cut your flux. So the MMF of the inductive coil is F is equal to Ni, right? Where N is the number of turns and I is the amount of current flowing through it. This is another formula for your magnetic field strength in which we talk about HL. HL is equal to Ni. This is also known as, this kind of law is also known as Ampere circuital law, in which we are talking about magnetic field intensity. There's a difference between B and H. B, capital B for ball. So B is basically magnetic flux density. Where is H? H by horse, magnetic field intensity. Okay, so that is your magnetic field intensity. Whereas your what I can say, B is magnetic flux density. I hope this is clear. B is magnetic flux density, and H is magnetic flux intensity. I hope this is clear. Yes, please. Is this clear? I hope there's a you are able to hear me up. I hope you are able to hear me up. Yes, you're able to hear me up. Okay. So when we are talking about F is equal to HL, HL is equal to Ni, and where which we're talking about the magnetic field strength and the length of the substance. We're talking about magnetic flux, number of magnetic lines of forces set up in a magnetic circle is called magnetic flux. So we know very well it is I hope this is clear. There's some kind of disturbance was coming actually. Okay. So terms during magnetic circuit, no magnetic number of magnetic lines of force set up in the magnetic circuit is basically magnetic flux. Okay, so remember this definition is very, very important. It is somehow asked in some interviews also. the number of magnetic lines of forces set up in a magnetic circuit. That is known as magnetic flux. So it is analogous to current. Okay, so we have a flux meter to measure this. Similar terms used in magnetic circuit, we know this phi. Phi is nothing but B into A. So we are having a B into A, that is flux is equal to B into A, surface area. And when we're talking about the surface area, it is B is equal to S into cos of theta. At theta is nothing but the angle between the plane, and this is nothing but Biot-Savart law. So magnetic field intensity of the magnetic field strength is the ratio, that is mu is equal to B upon H. And when mu is nothing but the permeability, we will see over here, you can see terms in magnetic circuits. We are having a current source and we are having a number of turns across the coil. And when this coil is having a number of turns, so naturally the MMF would be induced and H is equal to Ni upon L. These all formulas. This is very, very important slide in which all the four formulas are sitting written. On the right hand side, you can see MMF, H, B, and about relation between mu, B, and H. So you can see terms of magnetic circuit, you know magnetizing force B is equal to phi by A, H is equal to B upon mu naught mu R, right? So you can easily calculate A mu naught mu R easily, right? So terms of the magnetic circuit, according to the work law, HL is equal to Ni, we know very well, and H is equal to Ni upon L. This is a very, very important formula that we normally used. Magnetic reluctance, it is exactly same as the resistance, that is the resistance offered by to the magnetic flux, where the resistance offered to the current is basically resistance only, but whenever the obstruction offered by any kind of to the magnetic circuit or the magnetic flux, it is known as reluctance. It is given by S. You can see S is equal to L upon mu naught mu R A. Again, very, very important. This formula is again very, very important. L upon mu naught mu R A. Instead of mu naught mu R, we can easily write mu also. So permeance, that is permeance is basically the ease with the flux that can be set up. It is analogous to the conductance in electrical circuit, whereas reluctance was analogous to resistance. But in this case, permeance is analogous to conductance. Magnetic permeability is basically, you can see we are having two mediums and the current has to flow from one end to another end. So we will go with the particular magnetic permeability, that is mu is equal to B upon H. Then we will have terms in the magnetic circuits. You can see mu is equal to mu naught mu R that I will discuss with you. Mu R is a relative permeability, mu is the permeability in a medium, and mu naught is the absolute permeability. So that is the applications that we have in magnetic circuit. We use in speakers. Right now I'm using a speaker, so they are used in speakers, magnetic strip used in ATM cards, QR codes, tape recorders. Let's talk about another topic. This is very, very important in most of the interviews. Even in the IITs, this question is asked in some kind of Google interviews, some kind of interviews in the CSE branch, in the electronics communication. These are very, very important laws. Faraday's laws of electromagnetic induction. There are three laws. First law says whenever the current carrying conductor placed in a varying magnetic field. Please remember, whenever the current carrying conductor is placed in a varying magnetic field, the EMF is induced. And if the conductor circuit is closed, then we will say current will also be induced. That is known as induced current. I hope this is clear. Okay, so remember, whenever the current carrying conductor placed in a varying magnetic field, the EMF is induced. And if that conductor circuit is closed, then it will be the current would be induced. That is known as induced current. On the second law, induced EMF is equal to the rate of change of flux linkage. Please remember, second law first says whenever the current carrying conductor placed in a varying magnetic field, the EMF would be induced. Second is saying the induced EMF will equal to the rate of change of flux linkage. How much the flux is linked with the different number of turns. So that basically N into I. So product of N of the coil and the flux associated with it. Okay, so it would be the number of coil, N of the coil, turns of the coil, and the flux associated with it to it. That is E is equal to N phi. Okay, so if we talk about electromagnetic induction, you can say N phi 1 flux linkage, second is N phi 2, change in is basically N phi 2 minus N phi 1. Then we talk about flux linkage N phi, that is Weber per second. We can say rate of change of flux linkage, that will be N d phi by dt. And we will say N d phi by dt E is equal to minus N d phi by dt. So this is Faraday's law of electromagnetic induction, where the change of flux linkage is equal to induced EMF. So we will get E is equal to minus N d phi by dt. And the third law which will say is Lenz's law, which will talk about negative sign. So how can we increase the number of induced EMF? By increasing the number of turns or by increase the magnetic field, so that D5 would increase. So where we use this Faraday law, we will have a power transformer, the generating transformer, which because the power is generated or the energy is generated, the voltage is generated 11 kV. So we have to increase it. That is basically with the help of power transformer. Then Faraday law of mutual induction and electronic flow meters uses certain fluids also. So that's what we discussed. Introduction to magnetic circuits, MMF, magnetic circuits, application of magnetic circuits. So this is what is the some question can be asked. What is the difference between MMF and EMF? Define magnetic field intensity. What do you mean by magnetic permeance? Classify the types. We already know different magnetic circuits and application. So some questions. Ohm's law for magnetic circuit is, you know very well, V is F and phi is I and S is reluctance. So V is equal to IR. What happens to MMF when the magnetic flux decreases? It would also decrease because MMF is equal to N into I. What is MMF? Magnetomotive force. Equivalent of current is nothing but flux. These are some questions that we discussed in the magnetic circuit itself. So any kind of question you have, you can ask me. So we are come with the another topic, that is self-inductance and mutual inductance. So I will try to complete all the topics in one video, and then I will merge all of them, because sometimes when we are taking so much big video, it is very difficult to render them. So because you know very well how the system work, right? Okay, so coming back to self-inductance and mutual inductance. So in the previous topics, what we discussed about the Faraday law of electromagnetic induction. We discussed about how the magnetic circuit behave. Now we are going to discuss the self-inductance and mutual inductance. So we will discuss about Faraday law. We will talk about self-induction, mutual inductance, and coefficient of coupling. So this is how the basics of transformer that we are going to discuss about the transformer only. So you can see self-induction, mutual induction, coefficient of coupling. So when I'm talking about self-inductance or mutual inductance or coefficient of coupling, you need to understand they are connected with the inductor and two different conductors, or the dot convention. Sorry for the inconvenience. So you can see self-induction. It is defined as a property of the coil. Please remember, self-inductance or self-induction, it is a property of the coil which opposes the change of current flowing through it. So it's a property of the coil. It is not coming from outside. It is a property of the coil due to which it opposes the change of current flowing through it. So a phenomena in which the electric current is, in a circuit produces an induced electromotive force in an induced electromotive same circuit. So if the current in the coil increasing, self-induced EMF also oppose the rise of current. Okay, so you can say the induced EMF will be opposite to the applied voltage. That is the concept of self-inductance. Similarly, if your current is decreasing, the EMF induced in the coil in such a direction as to oppose the fall of current. Okay, so please, when the current coil, and remember two things. If the current in the coil is increasing, you will talking about the rise of the current. And if the current of the coil is decreasing, you're talking about the fall of the current. And induced EMF would be opposite if you're talking about the rise of current, and induced EMF will be same if you're talking about the fall of the current. That is very interesting. You can see E is equal to L di by dt. From this formula, you can see L is equal to E di by dt. At least the rate of change of current is decreasing. You will have your inductance would increase. That we already discussed. Similarly, you can see E is equal to L di by dt. So this is a wonderful formula. You have to keep remember this. L is equal to N phi by I. Now, how it come across? I put it Li instead, and L is equal to N. L is equal to, we take N d phi by dt, and then we compare both of them. And when we compare both of them, we get L is equal to N phi by I. That is very, very important. Where N is the number of turns, phi is a flux, and I is the amount of current. So in this formula, we are getting the parameter from the magnetic circuit. We are also having a parameter from the electrical circuit also. So this represents that yes, electrical magnetic circuits both can go hand in hand. Again, self-inductance. So what we come to know from the earlier discussion, the previous discussion, the value of inductance will be high if the magnetic flux will be stronger. The value of the inductance also depends on the material of the core and the number of turns. And we had a formula N phi by I. So higher with the value of inductance, the rate of change of current will be lower. So 1 Henry is equal to 1 Weber. Weber is nothing but the unit of flux, and ampere is a unit of so let's talk about mutual inductance. Now we're talking about two inductance coils, not one inductance coil. So it is defined as the property of the coil to which it opposes the change of current in another coil. Please remember, it opposes the change of current in the another coil or the neighboring coil. Now it depends how it is placed. It is placed adjacent. It is placed on the neighboring. You can see my video. I'm putting my some kind of expressions. It is placed on the neighboring, it is placed on like this. So it totally depends how the current is set up in the coil. Because of this changing flux, EMF is induced, that is known as mutually induced EMF. That can be positive, that can be negative, depending on the coefficient of coupling. So as you can see, two coils are there. In between, we are having a core. These lines are representing your iron core. If you don't have this, we will have a air core, right? So we will on the switch and turn on the A switch or B switch or S1 or S2. Multiple permutation and combination can be there. So E is equal to MDI by dt. Okay, so you can see that the mutual inductance is also increased, and if the rate of change of current is less. So mutual inductance can be C, EM and di by dt. Similarly, M and to di by dt. And when we combine both of them, we will get M is equal to N phi 12. If you're talking about M12, it is M1, it is M2, it is phi 12. If it is M1, it is phi 21 with respect to another pi. So what the major objective? Now you can understand if there are two different coils, that the flux linkage should be minimum to have your mutual inductance maximum. So how can we do that? We have to reduce our flux linkage, or you can be a leakage flux. We have to reduce the leakage flux. कम करना पड़ेगा. उसके लिए we have to make our concept of coefficient of coupling, so that both should be connected. So its value lies between 0 and 1, like a power factor. Is right. And if it is a fraction of coefficient of coupling, you can see L1 is equal to N. If I'm talking about L1, it is N2 phi 12. If it is L2, it is N1 phi 12, where K is nothing but a coefficient of coupling. The value lies between 0 and 1. Very, very important formulas. Please note it down. Okay. So if you're going to multiply both of them, so what the formula, which is important, K is equal to M divided by root L1 L2, where L1 is the inductance of first coil, L2 is the inductance of second coil, M is the mutual inductance, and K is the coefficient of coupling. So you know very well, if L1 L2 is very, very less, then the value of K would be high. So flux linkage has to be minimized. So you can see the K value of K would be 1 only if the flux produced by one coil will be completely linked. There's no leakage flux, and 0 if does not link and the leakage flux is maximum. What we discussed: Faraday law of electromagnetic induction, Lenz's law, concept of coefficient of coupling. So certain questions we can discuss now. So the law that induced the EMF, induced EMF current always oppose the cause between them is known as Lenz's law. Oppose. When we're talking about oppose, remember Faraday first law states that whenever the current carrying conductor placed in a varying magnetic field, the EMF would be induced. Second says the EMF would be the product of number of turns or flux linkage. The flux linkage is nothing but the number of turns into the flux, right? And third, which is nothing but Lenz's law, says it opposes. Okay. So open coil means no current would flow, so infinite resistance and zero inductance. As per Faraday law, the EMF induced by conductor whenever it cuts a magnetic flux. Whenever it cuts the magnetic flux, EMF is induced in the conductor whenever it cuts a magnetic flux. So the phenomena due to be there is induced current in a one coil, another coil, that is known as mutual inductance. So this is how the practice question, that was totally theoretical. I already told you. So go with the Lenz's law, self-inductance, mutual inductance, and Faraday law of electromagnetic induction. I hope everybody is clear about it. Please reply to me. If anybody have a query, you can reply in a comment section. Now that is we are talking about so introduction to transformer. In this we will talk about transformer itself. As you can see that we will go more into transformer. and we will discuss more of the things, right? So transformer is nothing but the outcome of Faraday law of electromagnetic induction that need to be understood. Okay. So there are three laws of Faraday law of electromagnetic induction. One says that whenever the conductor is placed, current carrying conductor is placed, I have to be more specific. Current carrying conductor is placed in a varying magnetic field, the EMF would be induced. Second says the amount of induced EMF, the value of induced EMF depend upon the flux linkage, rate of flux linkage. And third says that it oppose, so negative sign would come into the picture. That is known as Lenz's law. So let's talk about introduction transformer, in which we will talk about Faraday law of electromagnetic induction. We will talk about induced EMF, the working, their construction, the transformation ratio. So very important. Please stay in touch and see the whole video. So we will talk about Faraday law of electromagnetic induction. Again, the Faraday law first law says whenever the conductor is placed in a varying magnetic field, EMF is induced, and if the conductor circuit is closed, the induced current will flow. Right. So how can we ways to change the magnetic field intensity? We know whether we can rotating a coil, moving the coil, or changing the area. So changing the area is very difficult. We cannot. Rotating the coil relative to magnet, it's quite simple. And by moving the coil in and out of the magnet, in and out of the magnetic field is again good. So second law says the induced EMF in the coil is equal to the rate of change of flux linkage, as I already told you, that is N d phi by dt. Right number of turns definitely. So you can see that directional movement of there. There are different types of induced EMF, statically induced EMF and dynamically induced EMF, two types. Self-induced EMF and mutually induced EMF. So when I talk about self and mutually induced EMF, you can see it is E proportion di by dt, L di by dt. And L would be more if the change of current would be less. So that is a self-induced EMF. Mutual induced EMF that we already discussed. This is that how we can see we already discussed in the previous lecture. This is a mutual induced EMF in which the two different coils are there. They can be neighbored, they can be adjacent depending upon the position of the coil. The EMF induced, the value of induced EMF can be seen. So this kind of EMF is known as mutually induced EMF, in which we are talking about different coils. At least after this, we will talk. We come to the single phase transformer. So transformer is a static device which work on the electromagnetic induction only and used for transferring the electrical power from one circuit to another circuit without any variation in the frequency. That is very important. So it is only transfer of energy from one circuit to another circuit. That's the name is transformer. Transfer the resistance from primary winding to secondary winding. This is the working of the single phase transformer. As you can see easily, you have a transformer. The AC supply is provided over here. There's a primary turn, there's a secondary turn. The load is connected, and we are not able to know before the starting of the transformer whether this load is reactive, capacitive, or inductive. So that's why the rating of the transformer is in kVA, and we are having a electrical power transformer against the mutual induction itself. So it can raise the voltage or raise the voltage or decrease the voltage. So power transformer in mutual induction linked by a common magnetic flux that is being provided by the core. You can see we are having an iron core. So you can see it consists of two inductive coils which are electrically separated but magnetically linked through a path of low resistance, and that the path is given by your iron core. So you can see that suddenly the text changes. The two coil possesses a mutual inductance, magnetically connected. One winding is known as primary winding, second is known as secondary winding. Two type of transformers, step up and step down. You can see the transformer in which the output voltage is greater than an input voltage. It is known as step up. In which it is less than that, it is known as step down. So you can say T2 would be more than T1. Similarly, step down, in which we talk about the input voltage would be more than your output voltage. It would be step down. The number of turns would be similarly up and down depending on the type of transformer. If it is step up, the number of turns of primary would be less. In the case of step down, the number of primary secondary would be less. So on the construction of transformer, we have two type of transformer: coil type and shell type transformer. So when we talk about coil type and shell type transformer, they are, you can see we are having E and L type of laminations for a core type transformer. So there are two different type of losses in a transformer. One is eddy current losses and one is your uh, eddy current losses. One is your iron losses, basically eddy current losses, hysteresis losses. So two type of losses we normally have, iron loss and copper losses. So laminations are being made up so that they can be stripped down and they can butt it so that the circuit cannot be, the alternately stacked differently to eliminate continuous joints. Continue, we have to, but I can say we have to go with the discontinuity. Okay. So core tie transformer, you can see in front of you, the primary and secondary windings are interleaved with each other to reduce the leakage flux. The main objective is to reduce the leakage flux. Half of the winding is placed side by side and concentrate the leg of the core as shown as below. Right, separate limbs. You can see in a shell type transformer, we are having E type and central limb is there, you can see. Okay, so most of the central limb is having, having a major number of windings along the central limb. So it will carry whole of the flux and the side limbs is carry the half of the flux. The shell type transformer, as I told you, the primary and secondary are winding are placed on both central limbs. The low voltage winding is placed near the core and high voltage winding is placed outside the low voltage winding. The only objective, so that the efficiency or the lamination can be inserted. Okay, so and it also reduces the cost also, the insulation cost also. So the low voltage winding is always placed near the core and high voltage winding is always placed outside the low voltage winding. Transformation ratio N1 by N2, you know very well. We have two things, transformation turn ratio and transformation ratio. Both are opposite to each other. Turn ratio is N2 by N1 and transformation ratio is N1 by N2, as you can see in front of you. We are having application of transformer, two circuits isolate one with each other. So these are certain questions which can be asked. What actually transformer is? Do houses single phase supply? Yes. Principal transformer depend on the electromagnetic induction and mutual induction. Single phase transformer, but single phase means that it will use only one alternating supply. What is transfer ratio, turn ratio? You can see that turn ratio is basically V1 by V2 and turn ratio is transformation ratio is both are opposite to each other. Right? So that we studied. Thank you with the summary. Any query you can ask me. So in this PPT, through this PPT, in fact, we studied about the single phase transformer. We studied about what power transformer is all about. So any kind of query you can ask me. You can write in a comment section also. We are coming with the transformer losses. So transformer losses we will discuss is a very short topic. We will discuss the transformer losses. There are different type of losses we have. So we will discuss about the different losses. As you can see, we are having different transformer. One is ideal transformer, one is practical transformer. In the ideal transformer, we believe that there is no losses exist in the transformer. It's again a theoretical topic. Okay, and but in practical transformer, we do have certain type of losses, and those losses are segregated as iron loss and copper loss. So we are having a core losses and iron losses. So copper loss we have a stay loss, dielectric loss, how to reduce core losses, and we will discuss about the hysteresis loss. Without wasting time, let's start. So when we talk about the ideal transformer is one which is not having any kind of loss. We are having negligible primary and secondary winding resistance, infinite permeability. Infinite permeability means the core is pure magnetic circuit, zero leakage flow, no losses. This is the condition. Please note it down. This is very, very important for the ideal transformer. When I'm talking about losses of transformer, it is having iron losses, which can be classified into hysteresis and eddy current losses. And when we talk about copper losses, stay losses, and dielectric losses, so we have to, the minimum loss is basically iron loss, and we have to keep a copper loss equal to iron loss to have maximum efficiency. This is your core loss in the transformer. Hysteresis loss is basically it's directed to the magnetizing force, and we have to draw hysteresis loop. So basically, what core losses are all about, this is the core of the transformer and occur in the core. So that's why this is known as core losses, right? So you can say hysteresis losses are depending on, there's a formula noted down place. It's very, very important. A is a coefficient and eta is basically efficiency. B is the magnetic flux density raised to power 1.6. F is the frequency. V is the voltage. Eta is the proportionality constant I told you. So F is the frequency, supply frequency, V max is the maximum or the peak value of the flux density. Normally it is given in the question. When you talk about eddy current losses, whenever the flux linked with the closed circuit, the EMF is induced, I already told you. So the value of current depends on the amount of EMF and the resistance. So this kind of loss have to reduce by having laminations. And we are having different lamination as we already discussed in the previous topic, that we are having E and I laminations or L laminations. L lamination are used in core transformer, and E and I lamination are used, E laminations are used for your shell type transformer, right? So L laminations are basically used for your core transformer. Okay, and this is how we use it. So since the made of conducting material, so we are having Ke again coefficient. Bm is the maximum flux density, T is the thickness, F is the voltage, and F is the frequency, and V is the voltage. You can see that already shown in the slide also. Okay. So when we talk about copper losses, these losses are basically ohmic losses, depend on the transformer winding. If you are having negligible resistance, then we can say that we are having a negligible copper loss. Otherwise, we do have. Okay, and we are having I2 square R1, I2 square R2 respectively. So the total copper losses will be PC is equal to I square R1 plus I2 square R2. Stray losses depend on the leakage flux. So as soon as the load would more, the stray losses would be more, but it can be minimized by reducing the load on the transformer. Okay, so there the percentage of losses are very, very small. Dielectric losses are basically due to the insulating material. Whenever the oil get deteriorated or insulation get reduced. Already discussed, eddy current losses can be reduced by using laminations, and these laminations provide small gaps between the plates and reduce eddy current. Hysteresis, we have to change the material only, so that the least hysteresis loop area should be there, minimized loop area should be there. So how to minimize eddy current losses? Know very well. Thickness of material or less value magnetic flux density. Hysteresis, again less value magnetic flux density, and changing a material. So this is how your transformer we discuss about the losses. Any kind of query you can ask, or you can write in the comment section. So now we are having another topic, that is efficiency and voltage regulation. Again, very, very important. Normally, the transformer is having maximum efficiency because it is a static device. So what we are going to discuss by the transformer rating, kVA, efficiency, and frequency portion. So rating of transformer, stats of kilovolt ampere, we know very well. It's a unit of electrical power. Kilovolt ampere is basically apparent power. We are having three different types of power that we already discussed: real power, reactive power, and apparent power. Real power, which is basically consumed; reactive, which is basically generated; and this resultant is apparent power. So power in kVA and voltage and current, we know this, and kVA is a measurement of the equipment with the output power is independent of power factor. So that's why we are not able to, we don't have a load before the starting the transformer, so we are not able to understand. So that's why the measurement is in the unit of this is kVA. Independent power factor, efficiency, output or input power, so output power plus losses, V2I2 cos phi, V2I2 cos phi plus PI plus PC. We have to keep our PC equal to PI so that the efficiency can be maximized. Okay, we are having a secondary terminal voltage V2, full load secondary current, cos phi to power factor load. So this is a formula, very, very important. X is loading factor, V2I2 cos phi divided by X, V2I2 cos phi 2 plus PI plus X square, I square R RS, that is PC. Condition, the PI has to be equal to PC. There's a condition you can see, PC has to be equal to PI for maximum efficiency. So this is a load current, which is PI upon divided by RPC. Voltage regulation is the last topic of this video. Please understand this, and if you have any kind of query, you can ask me. Please feel free to ask. Voltage regulation is basically that whenever we are sending any kind of voltage, at the receiving end voltage, it should be same. If it is a deviation, that means we have a bad voltage regulation. Formula, you can see V no load minus V full load divided by V no load. Please note it down. V no load minus V full load divided by V no load. That is how the voltage regulation is being calculated, right? Then we talk about all-day efficiency. There are two efficiencies: all-day and commercial efficiency. All-day efficiency, you can see output kilowatt hour for 24 hours. whereas your commercial efficiency is not calculated like this, and it is more than your all-day efficiency. So what the formula I was talking about, you can see voltage regulation is V no load minus V full load divided by V in load. Application, we can use transformer, in various applications to stepping up the voltage, stepping down the voltage. It can also relate to circuit electrically. And what is the condition? These are some questions for max efficiency. Iron loss should be equal to copper loss. Voltage regulation, the measure of change in output voltage, magnitude between sending and receiving and voltage, it should be very, very high. If voltage regulation is 0, efficiency is maximum. If voltage regulation is 100, efficiency is 0. It is opposite to each other. Please remember it. It is asked in various interviews. Why the transformer rating in kVA? We know this. Iron loss in the voltage form and copper in the current form. There's a rating is in kVA. We can increase or decrease the value of voltage that we discussed in this video. I hope you understood. Right? Any kind of query you can write in the comment section. I would be happy, more than happy to answer your questions. Thank you very much. So with this, I'm signing off. Your guide, your teacher, your mentor, Dr. Kamal Kashyap. Thank you. Thank you very much.